Okay, in our last class, we found the inverse of a 2 by 2 matrix, and we found it 3 different ways, I believe. So, we're going to keep going with that. You do have a homework set for me, so if you have that homework set, just put it to the side, and I'll pick it up in a little bit. All right. Okay, so I'm asking you to solve this system of equations using the inverse. Now, on your test, I'm going to ask you this specifically. Now, we know how to solve these. We could use substitution, we could use Gauss-Jordan, we could use addition method, we could use all of those things, but I'm specifically going to ask you to find it using the inverse. So the first thing I'm going to do is write it as a partitioned matrix. I'm not going to write it that. I'm just going to write it like this. Let's say it this way. So I have my coefficient matrix, and I have my variable matrix, and I have my constant matrix. 2, 3, 1, 4, x, y. There we go. That's how it looks. Okay, so basically what I'm asking for is I am asking for xy. What does xy equal? And the way that I'm going to solve it, let's call this matrix A. I'm going to put an A there for a second. I need to get rid of matrix A to get xy by itself. Well, you can't divide by a matrix, right? So what you have to do with this is you have to take your A inverse and multiply it on the left side, because this A inverse and this A would cancel each other out. But what you do to one side, you have to do to the other. So we have to multiply A inverse on both sides of the equation. But specifically, we have to multiply A inverse on the left side of each equation. Because remember, matrix multiplication is not commutative, so you have to multiply it on the left side of each one. All right, so what we're going to do first is find this matrix A. I'm going to put it in blue. Matrix A is 2, 3, 1, 4. And we need to find the inverse. Okay, so to find the inverse, remember there's a shortcut way. To find the inverse, we're going to say 1 over the determinant. And remember the determinant is 4 times 2, which is 8, minus 1 times 3, which is 3. Okay. We are going to change the primary diagonal. So instead of 2 and 4, we're going to put it 4 and 2. We're going to swap those. And on the secondary diagonal, we're going to change their sign. So that would be a -3 and a -1. So cleaning this up, A inverse would be equaled 1 over 5 times this new matrix. So A inverse would actually equal 4/5, -3/5, -1/5, and 2/5. Okay, so that's my inverse. What are we going to do with it? So we're going to take 4/5, -3/5, -1/5, 2/5, and we're going to multiply it on both sides of the equation. You don't have to write all that up, but I did because I needed to show you what we're doing with it. So my A inverse would be that matrix, and we're going to multiply it on both sides. I'll give you a chance to get caught up. Now, if I did it properly, and let's hope I did, if I did it properly, I don't have to show this part because I picked it, right? And if I multiply A times A inverse, I'm going to get the identity back. So technically, I shouldn't have to do this left side over here. I shouldn't have to do that because hopefully I did it correctly. But I do want to double check and make sure. What I'm hoping happens over here on this left side is that everything cancels out and gives me the identity times xy, which would just give me xy. And we can double check it. Okay, so this would be 8/5, and then remember we're multiplying down, minus 3/5. So 8/5 minus 3/5 would be 5/5, which is 1. Okay, so then we'll go across. That's 12/5 minus 12/5, so that's 0. Row 2. That's a negative 2/5 here, plus 2/5, so that's 0. And this is a negative 3/5 plus 8/5, which is 1/5. So when I do multiply that left side out, this is what I get, which would just give you this. Okay, now you don't have to show me that side. I just wanted you to know where it went, what happened to it, and that's what happened to that side. Are there any questions with the left side? Okay, so now we'll go to the right side. So when I multiply the right side, I'm going to get 4/5 times 5, which is going to give me 4. And then I'm going to get 3/5 times 10. So that's a negative 35th, so that's a negative 6. So that part's going to equal a negative 2. And I get a negative 1/5 times 5, so that's a negative 1. Plus 20/5 would be 4, so I should get that. That's my answer. And that's how you would work it using inverses. I will certainly ask you one of those on your test, on your final, and on that homework set that I just gave you. So I'm going to ask you that 3 times as a graded assignment. Do you have any questions with it? All right, moving on along. Inverse. So all of those so far have been 2 by 2 matrices. But what happens when I ask you to find the inverse of a 3 by 3? Okay, there's no shortcut for this one. It's just bad. I'll just frankly be honest with you. It's a lot of work. Now, the only way to work a 3 by 3 is to adjoin it to the identity. So we'll call this matrix A. We're going to adjoin it to the identity. And that's what it's going to look like. In theory, this is what it's going to look like. So what we're going to do with matrix A is we're going to write it in reduced row echelon form all the way out. So on this left side, it's going to look like this. Okay, so we're going to take that matrix A over there. We're going to get rid of the 1s. We're going to go to the next column, get the 1 and get rid of the 0s. And then we're going to go to the next column, get the 1 and get the 0s. It's going to look just like this, which will take us, it could possibly take us 9 steps. Hopefully not, but it could. Now, when we do that, what happens is it turns things around. So we turn this A matrix into the identity, and what's left on the other side becomes the inverse. And that is where we're going. You're welcome. All right. There we go. Now you may get, we're getting to a certain path. You may get to a path a little bit differently than I do, and that's okay. If you combine steps, do steps all at once, whatever way you want to do it is fine. So what I'm going to do is I'm going to start with this 1 right here. I'm going to make it red. Okay, that's perfect. That's what we want to be there. But in order to make it in reduced row echelon form, I have to get rid of the zeros below. So I'm going to say negative row 1 plus row 2, and that's going to give me a new row 2. And I'm also, in that same breath, to save us some time, going to say negative 1 row 1 plus row 3 is going to give us a new row 3. So I'm going to get rid of this guy, and I'm going to get rid of this guy. Now, some of you can do it in your head, and that's fine too. I don't, because I make sign mistakes. But if you wanted to do it in your head, you could. Okay, the other thing I want to point out is when I say negative 1 row 1, it's going to go all the way across. You're going to treat it like it's 6 columns, not just 3. All right, double checking my signs really fast. So this is going to be 0, 1, 0, negative 1, 1, 0. Okay, and it looks like for this one, your teacher was pretty nice to you. Lots of things are canceling out. Okay, so that's the red one's going to be my new row 2. I'm not going to put it in just yet, but remember that we're not changing row 1 yet. Row 1's okay. We're using row 1 to get the other rows, but we're only physically changing row 2 and row 3. Those are the only ones we're changing in this step. I wish I could say, oh, they're always this easy, but they're not. This is like the easiest possible one of these I could give you. Everything doesn't cancel out and is all nice and neat like this usually. But it's good for our first one. So remember, we're trying to get the 1 and the zeros below it, so we did that. We need to move to our next column and get the 1, so we did that. It already has a 0 beneath it. That's great. So we're going to use that red 1 in the second column to get rid of that 3 above it. Because remember, we have to go all the way down to reduced row echelon form and not row echelon form. So this time, when I'm looking to get, I've got my first column, check. It's perfect. My second column's almost perfect. I have the 1 and the 0. I have to get rid of this 3. So the way I get rid of this 3 is I'm going to say negative 3 row 2 plus row 1 is going to give me a new row 1. And multiply it all the way across by negative 3. Like it. Okay, and you can see that if you got in a hurry, like hopefully I didn't, but I could have. If you got in a hurry and you miscopied something, or the board gives me stray marks from time to time, you just have to be really, really detail oriented. So now I have my second column done. I have 1 perfectly placed, and I've got zeros above and below. Then I go to my third column. I have the 1. I have a 0. I need that 3 to go out of the top one. Let's make it orange. I need to get rid of this guy. Okay, so I've been going super fast through it. Do you have any questions with any of the pieces? I'll give you a time to catch your breath and get things copied. Do you have any questions with what we're doing with it so far? Okay, so I'm going to use that last line, row 3, last row, to get rid of that orange 3. So I'm going to say -3, row 3, plus row 1 is going to give me a new row 1. When we get to this point, what is left is IA inverse. So this value here is your inverse. And that is how it would work. Now, like I said, that's the easiest one because a lot of that, a lot of them went to 0 in the middle. So that's, sometimes most of the time, in fact, they don't. Now, I'm not going to give you one like this on a test, but just for future reference, if you took one and you worked it out and you adjoined it to a matrix and you ended up with something that looked like this, if you get zeros over here like this, that means this doesn't have it. You can't solve that. There's no way to get a 1 in that back position there. So that means that this matrix would not have an inverse. Now, I'm not going to trick you like that with something on a test or something that's gradable, but it's in my notes, so that means it showed up somewhere at some point. So if you're working maybe at homework or something from the book or something you found on Khan Academy or YouTube, and you can't get a 1, because you can't turn a 0 into a 1, so if you can't get a 1 there and you get a solid row of zeros on the left side, then that's going to tell you it doesn't have an inverse. We did all that already. Okay, you have an inverse one on your homework assignment, a 3x3. Let's see what else we have.
Did you ever start recording?
Yeah, thank you. I did. Let's hope. Yes, I did. I know, right? Yes. Whew. We did start recording, thank goodness. I was like, I think so. I put it in my pocket, so once I put it in my pocket, I think we're good to go. All right, you should. I may not have given it to you. I haven't. Here it is right here. Our next section, our last section before our test, is section 2.4. Oh, maybe I hadn't even looked at 2.3 for a second. You have a sheet that says 2.3. Do you have this sheet? You may not, because I have a whole bunch of them.
2.3.
You have one that says 2.3 and it has all of the properties. You have that sheet? Okay. I have extras if you don't. And then you have a 2.4 sheet, which I don't believe I've given you. Two, 3. Perfect. Flip it over for me and see if it's anything in the back. Nope. There you go. There's your 2.4. Perfect. All right, on that 2-3 sheet, before you put it up, section 2.3 was all about the inverses. So it tells you on there that if it's invertible, it's non-singular, and if it's non-invertible, it's singular. And so one of the questions on your homework set for this week says, find X so that the matrix is singular, and what does singular mean? Okay, there's lots of things that singular means, but for this connotation, it's going to mean that you can't take the inverse, or there is no inverse. So singular means it doesn't have an inverse. Now, the way that you tell, especially a 2x2, so that one says find X so that the matrix is singular. The way that you tell if a matrix is singular or not by looking at it really quickly, a 2x2 especially. If we take the determinant and we get the determinant is 0, that means it's singular. And the way that we know that that one has no inverse is, remember when we get ready to find the inverse and we use my little switcheroo procedure, the first thing it tells you to do is 1 over the determinant times some matrix, right? Well, if that determinant is 0, that means you have division by 0, and you can't divide by 0. So that means if you have division by 0, then that means you can't take the inverse of it. So on that particular homework set, you're going to take that matrix, find the determinant, and see where X would make it 0. And then the part where singular means you can say the determinant is 0. Singular means that you can't take the inverse. There is no inverse. That it is non-invertible. All of those would be proper answers. All right. Any questions with that part? I think everything else on the homework set we've covered pretty well. Now then, while we're looking, let's also make sure before we go to the new section that I've covered everything on the worksheet 2 thus far. Let's see, where's worksheet 2? Here it is. Okay, we have definitely added, subtracted. We found the inverse now. We're good with that. Done that. Diagonal. Find the inverse. We did all that. Find the inverse. Use it to solve. Okay, so let's do one more just to make sure. Okay, I have been known, I try not to make it too tricky on you, but I have been known to ask this 2 different ways. I have asked before, find X so that the matrix is singular, and then I've also asked people to find X so that the matrix is not singular. So make sure you pay attention to the directions. Anytime I'm talking about singular, I'm going to be referring to the determinant. So if the determinant is 0, it is singular. If the determinant is not 0, it is non-singular. Okay, so be careful to read that part carefully on your test or quiz or homework or wherever you got it. All right, so let's find the determinant. So we're going to say that this is 60 minus 4x equals 0. So negative 4x would equal negative 60. Divide both sides by negative 4, and x equals 15. Okay, that would make it singular. And that's how you would answer. You'll say, okay, what would make it not singular? Anything that's not 15. You can write it like that, or you can say you can write in words, just like you said. Oh, you don't have to write it in. I don't make you write it in interval notation, because it's not a domain type thing. But you could say anything that's not 15 would make it non-singular. Right, and then now I think that finishes up everything through section 2-3. Do you have any questions with that? All right, so elementary matrices, those are next. An n by n matrix. We'll stop there. What does that mean? Yes?
It's a square.
Square, perfect. Both things you said were correct. It is a square matrix. A square matrix is an elementary matrix if it can be obtained from the identity by only one operation. Like it's one step away, right? Okay, so I give you 6 different ones on there, and your answer is going to be yes or no. Are these elementary? So take me a minute to write them. Okay, so you have 3 elementary row operations. Those are interchange 2 rows, multiply row by constant, or multiply by row by constant and add it to another row. So I'm looking, well, let's stick with our 3 by 3s for now. I'm going to look at these A, B, C, and D for a second. Can I get from the red matrix to the given matrix by one step? That's what I'm looking for. My answer to A is yes, I can. Okay, and so that means it is an elementary matrix. Now, the operation, you don't have to show it. It's just yes or no. Okay, now you're welcome to show it if you'd like. But the way that I got from I3 to A was I interchanged rows 1 and 3, which is a valid elementary operation. So if I put row 3 at the top, it looks like that. Yep, one step. Go ahead.
Does the single step specifically have to be an elementary row?
Yes. It's got to be one of those 3. Okay, so it has to be one. His question was, does it have to be an elementary row operation? My answer is yes. So it's got to be one of those 3 steps. Right? So that's our first one. The answer is yes. Any question with that one? All right, so the second one. That answer is also yes. It's a little bit harder to see. C, it's fast. You'd get that one in a heartbeat. But B is a little bit harder to see, but its answer is also yes. Okay, and so the operation that we used for this one is 5 row 1 plus row 2 gives me a new row 2. The other thing that's a little bit harder for you to see it, is up until today, up until this exact minute, you've been undoing, right? How do you undo a 5? And we're not undoing here. I'm just saying, how did you get from the red one to the 5? I'm not trying to undo the 5. So I got from this matrix right here, I3, to B by saying 5 times row 1, adding that to row 2, And this was my new row 2. Everything else is exactly alike. Row 1 is great. Row 3 is great. That is my new row 2. And I got it by this one little operation right here. Any question with that one? The answer to C is also yes. That's a little bit easier to see. What was that operation? 7 times row 2. Gives me a new row 2. Okay, and again, you don't have to, you're welcome to put that in there, but you don't have to show that part. All right, any question with that group? The answer to D is no. Because you have to do 2. So in order to get to D, you had to say 2 row 2 gives me a new row 2. And you also had to say -1 row 3 gives me a new row 3. And so that's 2 operations. And 2 operations is not valid for elementary. Right, so that's how those would go. Now, your next one is a 2 by 2. Okay, so that means we're going to be taking this matrix. There's my identity of size 2, and I need to get to E. What do you think?
Looks like it's a two-step.
Looks like it's a 2-step. Which 2 are they?
Swapping the 2 rows and then
Yep. 2 operations. Now, as far as which operation we did first, who knows, right? We could go either way. But it did have 2 operations. At some point, you said 3 times row 1, or you said 3 times row 2, but you said 3 times something. And then you also had to interchange rows 1 and 2 at some point for that 0, 1 to be in the top. Okay? So that's that one. So then you have your third one. What's the answer to that one? No. Why? It's not an n by m, which is a perfect answer, or you could say it is not square. And that is that one. Right, now these on the back, you flip to the back, but you're going to flip back to the front in a minute. We are going to factor matrices, and so that's what we're going to work on. We can't work on it today because I never start the hardest part at the end of class, and that is by far the hardest part. But I do need to talk to you about that and talk about what inverse operations are. That's on the front. You also, on the back, have Theorem 2.15, which is extremely, extremely important. I will ask it on this test. I will ask it on the final. I'll ask it on this homework part. I don't necessarily make you memorize all of them, but I usually ask you, give me 3 things you can say, or something like that. Here's what it means. Number 8 on your homework says, if A is an invertible matrix, name 3 other things that we can tell about them. Okay, so that's all going to come from this equivalent statement. So we know that if A is invertible on that sheet, then all of these other things have to be true as well. AX equals B has a unique solution. AX equals 0 has only the trivial solution. A is row equivalent to the identity. A can be written as a product of elementary matrices. There's another thing hidden in the clause at the top. It says if A is an n by n matrix, so it also has to be square. I also know, even adding more to that list, that if it's invertible, the determinant is not 0. I also know that. Now let's go ahead and talk about that theorem a little bit more, because it talks about some things that at the beginning of class today, I don't have it saved up here, but the beginning of class today, we solved this matrix equation. We got the answer 2, -3, I think. So we solved this earlier and we got a unique solution. We got one answer. So if you have an invertible matrix, and we remember we found A to be invertible, right? Because we used the A inverse. What it means to have a unique solution is that you can solve this equation and get one answer. And so that's how that plays into what we did today. You also have one that looks like this. Okay, and that's the zero matrix there, not just the number 0. That's a homogeneous system. It says that we know, because we studied this in our last test, that a homogeneous system always has a solution. It's always consistent. But we don't know if it has infinitely many solutions or if it has just one unique solution, which has to be trivial. So if we have A, that coefficient matrix there, if it has an inverse, this is said to only have one solution. And if it's said equal to 0, we always know that 0, 0 is a solution, so it has to be the trivial solution. Okay? So it has one solution and it's trivial, is basically what we're saying about that one. Row equivalent means that you can get from one matrix to the other by one step. I'm sorry, that's elementary. A being row equivalent means that you can take a series of elementary row operations and get from A to the identity. A can be written as a product of elementary matrices. That means you can factor it, which you see at the top of that page. All right, now what we're going to lead to on Wednesday is this. Flip back to the front for me. Okay, so we're going to make some operations, just like we even did today with our putting that matrix into finding the inverse of that 3x3 matrix, and we used our elementary row operations to simplify it down to get it to reduced row echelon form. We did some operations that, let's say, might look like this. We can interchange 2 rows. Okay, that's an operation that we're allowed to do. We can, another one, these are just some generic ones I'm coming up with. We could say 2 times row 1 and add that to row 2, and that gives me a new row 2. That's an operation we can do. Another operation that we can do is we can say 1/2 row 2, and that gives me a new row 2. You'll say, now where are you coming up with these? These are just some basic, just ones I'm just bringing up just to say, hey, these are some examples, some random examples out of my brain, random examples of elementary row operations. Okay, remember there are only 3 types. There's the interchange type, which is E1 here. There's the multiply one row by a constant, add it to another row type, that's 2. And the third one is multiply by a scalar quantity, and that's 3. Okay, those are your operations, an example of each. What we're going to do on Wednesday is we're going to do the opposite. So we're going to find an elementary row operation, and we're going to find its inverse operation. Now it's like this. Right now, in this little baby example over here, I'm multiplying by 2, and I'm adding 4. What's the opposite of adding 4? Subtracting 4. What's the opposite of multiply by 2? Divide by 2. So that's where we're going with these. I might be doing that over there. How do I undo it? That's where we're going. Okay? So if I switch 2 rows, what's the opposite of switching 2 rows? Switch them back, okay? So if you ever have this operation right here, interchange rows 1 and 2, the inverse operation is just to switch them back. That undoes it. Right, now, the way that you want to think about this one is you're subtracting 2. just like we were thinking about our basic equation on the other side. The opposite of subtracting 2 is adding 2. So we would do the same thing here, except instead of minus 2, we would say 2. Everything else stays the same, but instead of multiplying it by a negative 2, we multiply it by a positive 2. Okay, and that's because the inverse of subtracting is adding, and the inverse of adding is subtracting. So that's your add subtract one there. Your third one is your multiply divide one. So what's the opposite of divide? But this is 1/2, right? Multiplying by 1/2. That's like dividing by 2, right? So what's the opposite of dividing by 2? Multiplying by 2. Okay? And so those are going to be how we find our inverse operations that we're going to do on Wednesday. Let me peep really fast. On your little handout, your homework for this week, it will be due Monday. I got enough covered today. Yay. You can start working on this. You can't do number 9 yet on the homework assignment, but all the rest of them you can do.